on our notebook here. So we talked about calculating square distance function yesterday for temporal Gaussian process. So now it's quite straightforward that if we can calculate the square distance function spatially, we can do some Gaussian process spatially as well. So just a reminder, what is a square distance function? You are calculating the distance for each data point away from comparing to each pair of data points. So you can kind of calculating how far apart are they, and you can use their distance to calculate the covariance. This is based on the first law of geography. So it's kind of it's proposed by Toller, which is everything is related to everything else, but the nearest thing is more correlated than distant things. So we are calculating the distance, and we are assuming the nearby data points are more correlated than the distant data points. Okay, so here we calculate this square distance in spatially. So we are using this kind of geometry equation here. So you don't need to worry about this. So basically, if you go through this equation, it gives you a square distance matrix in space. Okay, it's a 1D radial distance. Okay, so you are just calculating the distance without considering the direction. Okay, we are not considering the direction. We are moving to the north or we are moving to the south. We are only considering that what is the radial distance between two data points. Okay, and it is calculated in radians here. Okay, so here we are using a data set from North America, the US Atlantic coast, and you can see the spatial distribution of this data point. Basically, we are moving from Florida to the north of Maine. So here you can run this. You can run the code along with me because some code is running pretty slow now. Okay, so here you can just calculate the square distance in terms of spatially. Okay, what's your input is two columns. One column is latitude, one column is longitude, right? And you are calculating the square distance function in terms of geographical space, and this is a function to help you to do that. So you're inputting to the column of your data point, and it will directly calculate the square distance function as a matrix for you. So here you can see the square distance function in terms of radius square. Okay, so you can see a little blob here, a little square here, because some of the data is collected from the same sites, so their distance is basically 0, and you can see that different sites have different square distance functions. Okay, I hope this makes sense to you. And why we are calculating in radians here? Because if you just multiply radius with the Earth's radius, you can get an idea of how much this radius corresponding to true geographical distance, which we'll talk about later. Okay, so now, okay, we are calculating square distance in terms of space, right? Then we just using the square distance function, inputting into a kernel, the same kernel we are using before, the RBF kernel. So here, previously, x minus x prime is our temporal square distance function. Now it's become a spatial distance function, and everything else is just the same. You can see here. Everything else is pretty much the same, right? So you can see that the nearby sites have higher correlation, and the sites away from this have lower correlation. or covariance. Okay. Okay. I hope this makes sense to you. And okay. So then we can build our very first spatial temporal kernel. So here, this is a spatial kernel, right? We were talking about temporal kernel before. So the most simple way we build a spatial temporal kernel is that we just multiply them together. Okay, so this is what we call a separable model. So a separable means you can kind of separate the spatial temporal in this case because we just multiply them together. A non-separable model means you have some space-time interaction. So in that case, you may have different spatial correlation in different time, or you may have different temporal correlation. I think it's like you may have different spatial correlation in different time, but that was much harder constraint considering how limited data we have in the past. So the most common, by far the most common kernel choices we use in paleo modeling is what we call a separable model, which is just multiplying the temporal and spatial model kernel together. Okay, because we are multiplying them together, you have 3 parameters here. One is the length scale for temporal space, and one is the length scale parameter for spatial space. And we have only one spatial. We have only one variance value for this kernel because if we multiply 2 variance together, we get 1 variance value. Okay, so in this case, you remember that for every spatial temporal kernel in PaleoSTEM, we have 3 hyperparameters. Okay, one is variance, one is spatial length scale, one is temporal length scale. Okay, so if we are talking about spatial temporal, we use big X here. Okay, so the input now is time and space, right? So the input structure is 3 columns. The first column is time. The second column is latitude. The third column is longitude, and the latitude and longitude is in decimal degree. Okay. So let's do our. Okay, I see a question from Emmanuel. So is there a restriction on the minimum geographical distance between 2 sites? No, Emmanuel, there's no restriction. So you can if you are inputting 2 sites, the geographical distance is 0. So that's also okay. So if your geographical distance is 0, you're inputting in the kernel, you will have a pretty large covariance value. Okay, so here, let me show you what I did here. So here, the input structure is X here. So it's kind of 3 columns, age, latitude, and longitude. So you do need to stack them together to make them fit into the PaleoSTEM data structure. And how do you generate a spatial kernel? It's pretty simple. So for every kernel, you have a function here, geo. It's called geo, which basically means geographic. So if you set geo equals true, the kernel knows that you are generating a spatial kernel. And the length scale here, it's called S length scale, which means spatial length scale. And 0.2 basically means 0.2 radius, which is corresponding to 1,200 kilometers in real life. Okay, so I do not set a prior here because I just use it for illustration, but in real project, you might set a prior for the length scale. Okay, and I set a temporal kernel here. I set geo equals false. If you do not set, the geo default is false. So the default to generate a kernel is a temporal kernel. Okay, so you might notice that for spatial kernel, there's no variance value. So the variance value is always equal to 1. So if you are trying to model only spatial space, you do need to change the source code, unfortunately. So, but I haven't met any people try to model only spatially. So if you want to model that, let me know. I will try to make it more flexible. Okay, so then we combine these two kernel together as a product. So we kind of multiply them together. We get a spatial temporal RBF kernel. So then for each kernel, we input x value, which is three-dimensional column. You remember, and we try to visualize that. Okay. So here is our temporal kernel. It looks like that. And this is our spatial kernel. And we multiply them. This one multiply element-wise multiply this one and this one. We'll get this spatial temporal kernel. Okay. How does this make sense to you? Okay, any questions so far? Okay, I'll give you 2 minutes to run this. Also, like you can change the type parameter here to see how does this impact your the resulting change the resulting kernel value. Okay, feel free to change any type parameter to see how does it change the resulting kernel. Okay, I got a question from Howard. So can you explain tensor 0.2 again? Why does it have to be 0.2? When do we need to change it? Okay, great question, Howard. So here, 0.2 means we have a spatial length scale of 0.2 radius. So this basically means the spatial correlation is the maximum. You can think about that was the maximum spatial correlation is 1,200 kilometers, right? Away from 1,200 kilometers, there's no spatial correlation between them. Okay, this is open to just an example value, so you can optimize it according to your data. But for different kind of process, you might have an idea, like you might have a domain knowledge that how correlated my data was, right? If your data is collected from different deltas, maybe you can think about that delta spatial coverage is like several hundred kilometers. So you can set this value according to your domain knowledge. Okay, I don't want my data to have a higher correlation than a few hundred kilometers, something like that. You don't have to be open to. Okay, so hopefully you're doing well. So let's move on. Okay, so now we are trying to fit this really simple spatial temporal kernel to our spatial temporal database. So we are building our first spatial temporal model. So here, let me show you how. Okay, so here the kernel kind of setup is pretty much similar. So you set a spatial kernel as an RBF, So you don't need to use RBF. We will cover that a little bit later. So here you set a spatial as RBF kernel, and we set our length scale to between 0.01 and 0.3 kilo, 0.01 and 0.3. No, it's radius. 0.01 means 63 kilometer, right? 0.3 means 1,900 kilometers in terms of spatial correlation. And we set our temporal kernel as well, pretty much similar as before. You combine the kernel and you put that kernel into your Gaussian process model. And here we are using noisy input Gaussian process and empirical Bayesian method to make the calculation a bit quicker. So here, for demonstration, I just make 50 iterations. So for your own project, you may need more iteration, because I use 50 because you see here the calculation become really pretty slow. The reason for that is Gaussian process scales cubically with data points. Okay, so here we have like several hundred data points comparing like previously we have like tens of data points. Okay, I encourage you to run this with me, so you don't need to wait too long later. Okay, so let me talk about this. So here is like I use like learning rates. So just an optimization trick. So learning rates means how quick you move for optimization. If you move too slowly, your optimization take a lot of iteration to converge. So this is kind of not what we want. If we move too fast, this may explode the optimization algorithm. So you will never converge as well. So I think the rule of thumb is you start with a intermediately large value like 0.1 here, and you let this learning rate to decay through time. So here, I just let it decay 80% of learning rates every 50 iterations, something like that. So that's why you can kind of start to learn quicker, and then it can try to converge with a smaller learning rate. Okay, so this is something you can apply if you have your own time. Okay, so here is our optimization curve. It's kind of optimized pretty well, like after 50 iteration, but you still see a kind of oscillation here and here. But if you see an oscillation in terms of hyperparameter, it doesn't matter that much. The most important thing we are trying to look at is the loss function here. Okay, 50 is clearly not enough, but like just for illustration, it's okay. Okay, so I want to explain a little bit more about what is kernel, ker0, ker1 means here. So if you are thinking about like our Gaussian process model, it contains a lot of kernels, right? If you think about this kernel is a product of a lot of kernels. So here ker1 basically means a specific kernel. So you can try to get it. You can try to get from the Gaussian process class. Okay, so here kernel0 basically means, I think basically means our spatial kernel, and kernel1 basically means our temporal kernel. But if you are combining a lot of kernel, like in our example later, we will use tens of kernels. So in that case, it may take you some time to find what is my kernel in terms of this kind of expression. Why you care about that? Because later you will try to do kernel decomposition. So you have to know which kernel you are trying to decompose, and maybe you try to set the hyperparameter in different kernel as the same value. So you do need to find out those kernel. I will show you a little bit later. Okay, so here, kernel 0 is a spatial kernel here. So the covariance for the spatial covariance function is always 1. Okay, so now we are trying to make the prediction. Okay, so here is a function we are trying to we have to provide an input value for this prediction, right? So the input value here is we input different time, but in the same space, in the same location. So we are trying to predict the temporal sea level change in one specific location, which is location 7. Okay, you can change the location from 1 to 15, I think. But here it's this temporal gap you are doing. So if you want to make the calculation a bit quicker, you can change it to 50. 50. So it can kind of give you the calculation times is much faster. Okay, it doesn't make too much difference. You cannot see that because our prediction is quite smooth. Okay, so you can change different sides, right, to see how does the including the spatial information impact on the prediction here. But here, I think site 7, I think it's a good site. You see here, if we are running pure temporal model, the model will go through this data point, right? But actually, if you see here, because we are considering the spatial correlation, the model doesn't go through these 2 data points because maybe the nearby data require the sea level to be a little bit lower here in this location. Okay, I haven't talked about how to calculate the sea level change rate, but here is a specific function you can calculate the sea level change rate. And the rate is 100-year average. So you can change that. Let me try to find the source code. Okay, the rate here is 200 years. It's averaging 200-year averaging sea level change rate. You can change that to 100. It's called CIF times that. Okay, you can make it 100. It's kind of rougher. You can make it 500. It's kind of more smoother. Okay, depends on the choice. Okay, but default is 200. Okay, so if you want to calculate the rate, you input age and the mean value you calculated before. Okay, this is using the PyTorch auto differentiation function, so you don't need to worry about what equation you are using. Something like that. It was automatically solved out for you. Okay, so we are predicting the temporal sea level here, and then we can do the spatial prediction as well. So here, spatial prediction, you see there's a lot of calculation here. So I will encourage you to make the calculation a bit faster. So you change the. So please change the code here to make the resolution a bit coarser. Okay, so here I will show you how that's happening. So here we are predicting two different times and a lot of different space. Okay. Here is like we have predicted 240 data points, so it should be all right. So remember that we're changing the spatial resolution to 2 degrees, and we're changing the temporal resolution to 4,000 years. So we are only calculating -1 at 10,000 years and -6,000 years. CE, yeah, and see what's the difference of sea level change. You can kind of, if you want to investigate any time and any space, you can just input as a three-dimensional column. So it's any time, any location, you can predict that. Okay, I hope that makes sense. So if we decrease the spatial resolution, it runs pretty quick. That's good. So please do not try to make the resolution higher, because if your notebook collapses, you do need to set up the environment again. So it's kind of annoying. Okay. So now you can see that we have a estimate of how much sea level change during this time slices. We have a estimate of how much sea level rates change. What is the rate of sea level change during this time range, and we have some uncertainty estimate. And as you'll see here, wherever you have some data, the uncertainty is lower, and the uncertainty get larger if you move away from those data. Okay. It kind of makes sense if you think about temporally. Whenever you have some data, the uncertainty is lower, and when you move away, if you don't have data, the uncertainty gets larger. Okay, I hope this makes sense to you. So again, this kind of experiment is discussed quite a lot in Erica Ash's 2019 paper. So if you haven't read this paper before, I strongly recommend it. You should read this paper written by Erica Ash, which where she talked a lot about statistical modeling in Holocene sea level change. There's a lot of theories covered in that paper as well. Okay, so I hope that makes sense to you. So that's